Hello. What I'd like to do in this video is go through a couple of documents that I prepared to help you out on your final exam. What I've found is that if I'm able to provide a summary of the equations and some of the common figures and tables that you'll need on the final exam, that it helps speed the process up, especially since it's a timed exam. The other thing that this is useful for is for helping you actually study and prepare for the final exam. If you understand what is in both of these documents, generally speaking, as far as the math problems are concerned on the final exam, you should be able to use these resources and not have to actually go and find your textbook examples and problems and equations. In other words, everything you need to work out the problems as far as calculations are concerned should be available within these documents. So I recommend that we spend a few moments going through this and make sure that you're familiar with what's in here. This doesn't necessarily take away from you needing to go back and use that other material as you prepare for the final exam. I recommend using this in conjunction with your study for the final exam as you go through these. What I like to do is first off start with the equation sheets. I've got four pages of equations here for you. I begin with general formulas, and then I jump into some timber formulas, some steel formulas, and some concrete formulas, and you'll see it organized that way. It also generally follows the sequence of this semester as we progressed from start to finish. And so on this first page right here, with the general formulas, we begin with the general trig properties. And anytime we're working with vectors and we need to either resolve the components of the vector or to find the resultant force from the two components, then these would be the equations that we'd utilize. And so if we're looking for the components, we've got this equation right here to help us. And if we're looking for finding the resultant force, then we would use these right here. And I think that's how you spell Pythagorean theorem. But essentially all you're doing is using Pythagorean theorem to solve the angle of the force or the actual resultant of the force by squaring the components, adding them together and taking the square root. If you're given a composite shape and you needed to deal with finding the centroid of that composite shape, these are the two equations. Remember, we call them x bar and y bar. You're probably more used to seeing something that looked more like this. The summation of the xa's divided by the summation of the a's, or the summation of the ya's divided by the summation of the a's. I think this is the way I wrote it on the board in the class, but for the sake of this problem, I've written it out in a little bit longer form so that you can follow through with that and remember exactly what you're doing there. Remember, we did this in table format typically. When it comes to solving the moments of inertia, there were a number of different equations that came out of the book. I've only included one here, and this is the moment of inertia for a rectangular shape, just the base times the height cubed divided by 12. Remember, it's not base times height and then all of that cubed. Take your height cubed, multiply it by your base, and then divide by 12. Similarly, if we needed to adjust and account for any offset that we had with the centroid not passing through the composite shape neutral axis, then we'd also have to use the parallel axis theorem, where the moment of inertia values from the equations all get summed together, but we also have to account for the distance away from the neutral axis that these lie. And I'll let you run back and go through that. When it comes to the stress equation, this is the general stress equation. Stress equals the point load divided by the area. This is simply the axial force divided by area. Stress equals force divided by area in general. And we'll see a couple other stress formulas here in just a moment. As far as axial deformation, this is just a fancy word of saying what is strain. Strain is equal to the change in length divided by the original length. that we had there. This is also, by the way, stress and strain. I put stain. I can't spell. Let's try writing that out again. Strain. There we go. Stress and strain ought to be two formulas that you remember off the top of your head. And I do have them here in case you had to calculate something. But by definition, you should actually remember those. Modulus of elasticity is a term that we use quite a bit. This is the material stiffness. If we had our stress strain curve and we were to plot what that looked like, the modulus of elasticity is the slope of the linear portion of that curve. And so we would have the stress divided by the strain that gives us that actual slope. And so again, it's the material stiffness. By the way, I didn't say this earlier, but with moment of inertia, it's also considered a stiffness, and we refer to it as the shape stiffness because it also gives us some strength depending on what the cross-sectional shape of the member is. Flexural formula is just a fancy way of referring to bending stress. And so this is the way that we calculate actual bending stress. Note that I don't have bending stress written down here in the definition, but you should remember that little f is for the actual stress, b for bending. And from the equation, we can see that m would be the maximum moment that we'd be interested in. And you'll recall that if we're dealing with a rectangular shape like this, that we could calculate the moment of inertia for that shape, and then the c value would be equal to the distance from the neutral axis up to the extreme fiber. And if the neutral axis was not through the center of the shape, then it would be the larger of the two values. The section modulus is just a fancy shortcut that we use to reduce where it is equal to the moment of inertia divided by that distance from the neutral axis to the extreme fiber. And so it's typically you're going to pull the moment of inertia or the section modulus from one of the tables in the appendices. But I've included both equations here in case you want to deal with both of those. When we're dealing with shear stress, we use the shear formula. And I've included two equations right here. The first one is the general equation. You'll recall, go back and check in your notes if you need to follow through this again, but if we're splitting the shape down the center, and we were looking for the shear stress at the center of the beam, then we could take the top or the bottom part and split it out. So we'd have an area below right here. And also the distance from the neutral axis to the center of that area is equal to, I think we called it the y, I think it was the y bar was the term that we actually used for that. And you'll remember that Q equals A times Y bar. And that's noted here. The area above, technically I've drawn it as below. So let's just make a note here. Or below the shear stress times the distance from the neutral axis to the centroid of the same area. V equals the maximum shear. I equals the moment of inertia for the shape, in this case a rectangle. And B equals the width of the beam, width here. And so it's pretty easy to crank math through for easy shapes. If you've got a more complicated shape, it'll take you a little bit more time to do that. You'll recall from doing that on the homework. If you've got a rectangular shape, then we can reduce this equation down, and it's simply 1.5 times the shear value divided by the area of the entire cross-section for that rectangle. And this significantly speeds up the process when we're dealing with something like that. I've got two other equations on this page right here. We've got, if we're doing the LRFD technique, which we used for concrete and steel in the class, remember there's a whole bunch of different factored load cases that we might consider, but we use these two cases right here. 1.4 times the dead load, or 1.2 times the dead load plus 1.6 times the live load. And whichever is the larger value, then that's the one that governs. That's the value we would go ahead and run through our process for calculations. So, all right, let's jump down to timber design equations. I believe there's actually more information on this page than what you'll need on the final exam. This is the actual page that I had posted on Learning Suite to help march you through the process. I'm not going to spend a whole lot of time on this page right here. I will remind you that by definition, the slenderness ratio for a timber column is the length of the column, technically the length of the unbraced part of the column, divided by the width of the member. And you'll recall that for braced columns we had to check the strong axis and the weak axis. This is the compression formula right here, where we simply have the point load divided by the cross-sectional area. This is simply a compression stress value that shows up. But we call it compression F sub C rather than F sub V, general stress, simply because we're dealing with compression of a column. If we're dealing with bending and shear, we've already introduced those formulas up above. And then the rest of this right here, this simply has to do with the process of calculating specific for timber columns. And you'll recall that this right here was the process we used for doing the compression capacity of a column. Of course, we had to use the Euler buckling equation right here, and then the F sub C star equation right there. Take the ratio of those, and we jump over to a table, pull a factor to get our column stability factor, and then we plugged that back in up here. That process took quite a while. I actually, on the final exam, don't have you march through problems that go through entire processes like these, just because it's so time consuming. And so generally speaking, you should be aware of individual formulas and how to use them, but you shouldn't have to go through the entire process. I don't also have you calculate the interaction equation on the final exam, simply because that process was quite lengthy as well. Basically utilized everything else on this entire page, plug it in, make sure its value is less than 100% or the value of 1. But in general, be familiar with what this equation actually means. Be familiar with the equation. All we're doing here is we're taking the compression stress that actually exists in the column, and we divide by the compression capacity. We also take the bending stress that actually exists in the column, divide by the bending capacity. I know there's a bunch of extra stuff in here. That's just the empirical form for timber, but it's the actual bending stress capacity that exists. And then we add those together. So in short, it's the critical combination of compression and bending capacity that we're dealing with in the interaction equation. We only ever did the interaction equation with timber, but you should note that we do consider interaction with steel columns as well as concrete columns as well. I've significantly shortened the steel design equation sheet that I posted initially. I had a video where I went through quite a bit of information on there. I've condensed it down to just these 4 equations right here. One is the bending moment capacity at yield stress. And so this would be for the elastic form of the equation. If we're dealing with the plastic form of the equation and need to find out the limiting moment that exists there, we would use this equation right here. And these 2 equations help determine what loads are allowed on the common to remain in the elastic range, or if we go beyond the elastic range for extreme loaded conditions, what can we then expect within the plastic range and not fell our beam? This equation right here is by definition the LRFD equation. On the left side of the equation we have our failure, and remember we apply a factor that reduces failure, and then on the right side of the equation we have our loads that we anticipate, and remember we throw factors on that increase those. And as long as the factored failure is still greater than the factored loads, by definition for LRFD, that's the design process that we utilize to make sure that everything is designed correctly. Boy, I'm misspelling all over the place today. F-A-I-L-U-R-E, failure. All right, for shear calculations, remember we had several other cases on there. I've gone ahead and just removed the other two cases. This is our case 1 failure right here. And if this holds true, then we use this equation right here. Couple quick things to remember about this equation right here. We're dealing with a wide flange section. H is the clear span between the flanges, so it's the height of the web, and the TW is the thickness of the web. Essentially what we're doing is we're calculating the slenderness ratio of the web. And if that case holds true, relative, this is the yield strength of the steel. If that holds true and it's case 1, then we utilize this equation right here. And the only other thing you need to remember is that the area of the web is an approximation where we go ahead and we use the complete height of the beam, D, and we multiply that by the thickness of the web. And so we're utilizing that, essentially leaving the flange section out and considering all the entire height of the web and flanges as the shear carrying capacity of the steel. With concrete design, if you watched those videos that we went through in class, you remember we didn't really have any homework associated with that, but there was a couple key equations that you should be familiar with. Of course, I'm writing them here in case you need to use them for the test. Hint, hint. The maximum spacing for a concrete beam, remember that a concrete beam is typically rectangular for the general case. And if we've got our D being a certain height, let's call it 20 inches right there, then the maximum spacing for our shear reinforcement, I just said max spacing, but this is for shear reinforcement, is D over 2, so that we have at least 2 of those rebar that a shear crack that would potentially develop would have to cross through. So if the height was 20 inches, maximum spacing is 10 inches. There is a spacing equation that sometimes says we've got to get them closer than maximum, but I've only had to deal with maximum. When we're dealing with column design, right here, remember the eccentricity is, we went through this on the other video, but when we're dealing with a general moment equation, moment by definition is force times distance. And if we need to figure out what the distance is, then that's simply the moment divided by the force. And you'll recall that eccentricity is just a fancy way of saying that there is some distance. If we've got a column right here, and this is the center of my beam, and my force is actually acting some distance away from the center of the beam for whatever reason, that's what we call the eccentric load, or the eccentricity. It's really just the distance. So to find out what that eccentricity is, we take the moment divided by the force, but because we're dealing with LRFD, don't forget that these are factored moments and factored loads. And I went through an example with a concrete that talked about how to do that. All right, there you go. There's your equations. If you know how to use these equations, you should be able to get through the workout problems on the test. Now, some of those may require some tables or figures or additional equations. And so I've included, now by additional equations, I'm talking about the common shape solutions, or sometimes the figures will have equations embedded in them. And so I've included another document that I call the figures for the final exam. And you'll notice that the first 8 pages are simply the common shape solutions. And so as a quick reminder, you've always got on those the definition of what that is. I don't always show a picture of what it is, but in this case it's a simply supported beam with a point load in the center. You've got an equation for shear, you've got an equation for moment, and you've got an equation for deflection. And each one of these follows the same process. Simply supported beam with a uniformly distributed load, shear, moment, deflection equation, and we follow that through on each page. Couple quick things to note with this. Anytime they've got a fixed end, in this case it's a cantilever beam with a fixed end, I've drawn it with a fixed symbol, so you can follow that. This is one place that students tend to grab the wrong equation. If you've got a fixed beam, fixed on both ends, make sure you're on the fixed beam diagram, because if you come back up here and you're not paying attention to the end points, then the simply supported beam looks very similar, but in this case there's no fixed end points showing up in the diagram. So make sure you're on the right diagram. Another one that gets mixed up with a cantilever occasionally is a propped beam. In this case, a prop beam has a propped reaction and a fixed connection. Looks an awful lot like the cantilever, except that it's got the propped portion on there. Of course, with these diagrams right here, I don't have deflection equations for these later diagrams, but you do have the ability to calculate what the maximum shear is and the maximum moment. And when you come to the moment and the shear diagrams, I've drawn them to scale as best as I can, but you've got to actually look at which of these values is larger. 0.188 PL is larger than 0.156 PL, therefore this one would be the maximum. And you do need to look across those diagrams and figure out where the maximum is. Recall that we've also got a continuous beams, so we've got 2-span beams with distributed loads or point loads, and then I've also got a continuous beam. This one's actually not labeled. Oh, there it is right there. Continuous beam with a 3-span uniformly distributed load. And again, you can figure out where the maximum moments are and where the maximum shears are from those diagrams. All right, one additional general table before we jump into timber, steel, and concrete specific tables. I believe this is table 5.2 out of your textbook. If we're dealing with trying to find out what the allowable bending stress is, or the allowable shear stress, or even the allowable axial compression, I believe those are the ones that we utilize most often. And we need that generally for 36 KSI steel, 50 KSI steel. We occasionally, I think we had problems where we used glue lam beams or something like that. Or generally for the timber sections, you can utilize this table to get your baseline value. You can also use this table to find out what the modulus of elasticity for those materials are in this column right here. So pretty easy to grab a value off this table if you need it for an equation. Remember, a lot of those equations have moment of inertia in there. This value, this is where we start the timber design figures. I turned the figure sideways. Normally when I print these in paper, when the students used to do the final in class, it made sense. You could just turn the page. But in this case, I've gone ahead and rotated the paper, and that's why that shows up sideways right there. I don't especially like this table, 5.2, for the timber properties. I actually like using this table because you'll see that it breaks it down into more specific values depending on the shape of the material, meaning the cross-sectional shape, and the grade of the material is broken down significantly with more depth. And so the only key to remembering how to read this table, you've got bending stress and shear stress and compression if need be. Recall that dimension lumber is anything that's 2x, 3x, or 4x, whatever. 2x8, 2x10, 4x8, 4x10. Those are all dimension lumbers. If I'm using beams and stringers, those are rectangular. So take the first dimension of 5x and add at least 2 inches, and that makes it rectangular. And so 5x7, 5x8, 6x8, 6x9, etc. Those are beams and stringers because they're rectangular. Posts and timbers are typically used for columns. By the way, these are usually used for beams, as shown there. These are square or nearly square when we're dealing with posts and timbers. So again, start with a 5x5 or a 5x6 would be considered a post and timber, and we would utilize this part of the table to grab our value. And then, of course, you've got to pick the correct grade off of there. And I will specifically call out one of these terms that show up here. So a stud grade, a number 1 grade. If I want you to use number 1 and better, it will say number 1 and better. Okay? Otherwise, it's pretty easy to grab the values off the table that you need there. This was the table, or the figure that we used for column stability factor. If you need to grab a column stability factor off of there, remember you've got the ratio of Euler buckling to the adjusted compressive stress. You just take that ratio, grab a value wherever it is, and then you've got sawn lumber and glue lambs, depending on what type of column you're dealing with. That gives you the specific column. And of course, you've got 4 different, it's really one giant column split into 4 different sections. And it's pretty easy to jump in there and grab your column stability factor off the table. Out of your appendices, if you need some shape properties, meaning the geometric properties for either dimension lumber or beams and columns, then so you've got your 2x, 3x's, and your 4x's up above, and notice there's no 5s. It just goes with 6x's, 8x's, 10x's, or 12x's down below. Then you can jump down into this section here, and remember there's both English and metric units in here. So you've got the actual dimensions, you've got the cross-sectional area, you've got the section modulus, and you've got the moment of inertia values that all come from these tables right here. This particular diagram showed up with our timber properties. Remember that with timber, if the load is on there for a short duration of time, then the timber actually has more carrying capacity, and we ended up increasing by a factor of 2. This is our load duration factor, whereas our default value is the 10-year load, and it's got a duration factor of 1.0. So if we've got a load on there longer than 10 years, a permanent load we call that, then we actually reduce it by, or you multiply it by a value of 0.9, which reduces it by 10%. And so pretty easy to grab the values off here. You've got wind and seismic, you've got a 7-day load, a snow day load, and there's your 10-year load and your permanent load. And of course, the corresponding values show up over here, 1.6, 1.25, 1.15, etc. This was the size adjustment factor that we gave you as a supplementary material. I believe I've got a problem on the final exam that just asks you to pull the size adjustment factor. If I'm dealing with the bending stress size adjustment factor, we're going to use the middle section of the column. If I'm using the compression stress, then we would use this outer column that we're dealing with here. This table only works for dimension lumber, and so you've got 2x or 3x whatever and 4x whatever. With the compression capacity, 2x, 3x, or 4x is all the same. And then the only other thing you have to consider here is stud grade is the bottom part of the chart. Everything else is the top part of the chart. And so I would define for you, you're dealing with a 2 by 10. You're looking for bending stress values. So 2 by 10 for bending stress. And then we could pull our adjustment factor from there. This particular diagram or table, if you recall, is for load capacity. I often will use the bottom part of the chart if I'm attaching a 1 by something or a 2 by something. Then we can determine which part of the table we need to utilize. Then we usually define it by the size of the nail. And so if I'm attaching a 1 by 4 with 10 penny nails, then there's my load carrying capacity. Don't forget that this is load per nail. And so if I had 2 nails in that particular connection, 2 10 penny nails holding a 1 by 4 to something, then my capacity be 105 times the 2 for the nails, or 210 pounds. Pounds is there for our units. So you can use the chart either forward or backward, depending on what you're trying to utilize it for. All right, steel design figures. This is also from your appendices in the back of the book. I believe this is table A3. Don't quote me on that. It says it right there, table A3. You can quote me on that now because I remembered. Remember, table A3 actually went on for pages, and I've given you the one specific page that you would need to utilize on the test. So it's got some W18 sections, some W16 sections. And from this particular table, once you find out which size you're dealing with, you can get the cross-sectional area. You can get all the geometric properties. So there's the total height. And you've also got the flange properties and the web properties right there. So these are the geometric values. You've got the total height, the width of the flange, I should say the total depth, the height of the web section, the thickness of the web section, and the thickness of the flange section. And all those values are shown within here. The other properties that show up here are for the strong axis or the weak axis, and you've got moment of inertia, section modulus, and the radius of gyration. And so we utilize the radius of gyration for columns and moment of inertia or section modulus for columns or beams. And again, you've got strong axis or weak axis values that show up in here. This is another steel property table that shows up. This one is specific to table A11 out of the appendix. This one is specific to when we're dealing with the plastic hinge or the plastic failure limit for the steel beam. And so everything is sorted according to the plastic section modulus. And so in there, then you can read off what the different sections are that show up, W18 by 55, etc. And it also has all the geometric values that show up in that particular chart. You could actually pull these same values. If we came back here to W18 by 55, you should be able to pull the same geometric information. It's just in this case, it's all sorted based on that plastic section failure. The other thing that this particular chart does is it gives you what the limiting capacities are when we're dealing with plastic failure out here. One other final thing to note on this chart, the way that we often utilize it, is if we determine that we have a plastic section modulus that we calculate it and we determine that we need at least 40 KSI, or sorry, I said the units wrong. I knew I was going to do that. 40 inches cubed as our section on there, then anything that is larger than 40 will work. But remember, we typically use the smallest or the lightest weight section. So a W14 by 26 is the lightest within this little section right here. But if you jump up, you'll notice I got a W12 by 30, a W16 by 26, etc. You can quickly scan up. Ironically, in this case, a W14 by 26 and a W16 by 26 have the same weight, and so we would actually choose the W14 by 26. If by chance we decided that we needed something that had 100, you'd come up here, and I'm not picking examples very well. I did the same thing. Let's go down and pick a value that has 80. 80 will work for me. I'm trying to demonstrate this. Sometimes there's a lighter section above. W16 by 45 is the first one that works, because 82.3 is barely bigger than 80. But if you scan up real quick, there's actually a W21 by 44 that is lighter. And assuming that we have the dimensions to fit a W21 in there, for the sake of this class, I said go ahead and pick the lightest section. It's going to be cheaper. That's the value that we'd select. All right, column stability factor. Column stability factor, if you recall, is simply a function of calculating KL over R. K was the adjustment for the end connections. K is typically 1.0 if we're pinned. There are some other values that show up if we're not pinned. L was the length, and R was the radius of gyration that comes from our geometric properties. And you can quickly calculate what the KL over R ratio is, and then pull off of there the allowable stress. And this gives us the stress limit of what we're dealing with. All right. When we did our connection examples, this is one of the charts that showed up. This is specific to calculating the shear capacity of a bolted connection. And so if we're dealing with bolts, then we'd pick the specific type of bolt I've given, A307 or A325, A490. All this information would be given in the problem. I would tell you the connection type. Maybe I'd say it's an X with a standard hole type. And then the only other things that you'd have to make sure is, in this case, it would be a single shear connection. If we're dealing with a double shear connection, then it would be an NSL hole type. And then we would pay attention to what the diameter of the bolt is. And in this case, if the example was a 1-inch diameter bolt for A325X standard hole size, then the actual load per bolt would be 23.5, and the units are kips in this case. So don't forget this is per bolt, and so if I had 2 bolts, then you would have to actually multiply that by 2. And so that chart works similar to the other one. Here's our weld chart that we pulled from the book. It's table 10.5 from the book. Pretty easy to utilize. If I give you a certain weld size, let's say we're using a 1/2-inch weld, then for every inch of that weld, I can handle 7.42 kips per inch. And the only thing we need to know is then how long the weld is. And if that particular weld is, let's say it's 10 inches long, then the total capacity of that weld was 7.42 times the 10 inches, or 74.2 kips. All right, reinforced concrete design figures. That's the last section of this. This particular table had our bar sizes with the corresponding diameters and cross-sectional areas if we needed something to pull from there. Remember that typically up to number 8 bar, the diameter corresponds with the number of the bar divided by a factor of 8. So a number 4 bar would be 4/8 or 1/2 inch. And of course the cross-sectional area just saves you a little bit of math. The next 3 tables or figures have to do with the embedment length. And this particular one is the embedment length for hooked bars. This one right here is for tensile reinforcement, but we're dealing with standard bars versus top bars. I don't actually have the compression table on here. There's another table that you utilized on your homework. I've just narrowed it down to these three to simplify and kind of condense the charts a little bit. With most of these, don't forget that there's always a little bit of a footnote involved. This particular chart is perfect for 180-degree hooks, meaning a hook that looks like this. But if I have a 90-degree hook, then I've got to reduce the value that shows up in the table by 30%, and so we multiply by 0.7 to actually get that. All these figures work the same in that you're given the strength of the rebar, the strength of the concrete, and the bar size, and from there you can just pull off whatever the reinforcement required development length is. If it was all this value and we end up with 15 inches is the unit there, that would be how long we'd have to embed that. Of course, if it was this style of a hook, a 90-degree hook, we'd multiply 15 by 0.7 to get the answer. Both these tables read the same. The only exception is you got to remember which one we're dealing with. For standard bars, it's easier to define the other way. Top bars are for horizontal members that have at least 12 inches of concrete below the bar. And so we're talking about a beam that we've got reinforcement in the top of the bar and at least 12 inches of concrete below it. If that's the condition that we're looking for, that's considered a top bar. We would go ahead and we'd utilize this figure. If not, we would, and we're looking for tensile reinforcement, we'd go ahead and utilize this figure right here. This is the column chart that we talked about. Gave an example at the tail end of the reinforced concrete section. Pretty easy to utilize as long as you remember what you're calculating here. This one is the factored compression load. Remember factor, it's 1.2 times the dead load plus 1.6 times the live load, or 1.4 times the dead load. That's how we factor the compression load. Whatever value we get on there, then we have to plot that against the eccentricity. We gave you the equation for eccentricity just a handful of minutes ago. Eccentricity equals the factored moment divided by the factored compression capacity, or the factored load. And don't forget that this plots in inches. More often than not, the values are in kips and feet up here, and so your answer comes out in feet, and you need to make sure and convert it to inches to plot on this chart. All right, there you go. There's the figures and tables and equations that you can expect to utilize on the final exam. I would use this as a studying point, and make sure you know how to do and use everything in here. I've tried to walk through and remind you what everything is, and give you some tips and tricks and pointers on how to use this. Because the final is timed, don't plan on spending a lot of time figuring things out during the final exam. Make sure you're familiar with these ahead of time. And if you know how to use these figures and tables, you should be able to get through the workout problems on the final exam fairly readily. All right, good luck.